Right, so we left off with the uniqueness theorem, which, just to remind us where we left off, we said that if two random variables have the same moment generating function, and both of these moment generating functions are finite in a region of zero, in an open set around zero, then the then x and y have the same distribution. And we said that this was hard to prove in general, but we could prove it in a special case. And the special case was in the discrete case, non-negative integer valued random variables. And the reason we could do that is because of a connection between moment generating functions and probability generating functions. In the discrete case. Okay. So remember the definition. We're going to let x be a discrete random variable with probability mass function p sub x such that probability that x is non-negative is 1. So it's a non-negative random variable. And probability that x equals k is the mass function evaluated at k for non-negative integer values k. Then the moment generating function of x is the sum from k equals 0 to infinity e to the tk px k. And if we were to put s equal to e to the power t, then if we define gx of s equal to k equals 0, s to the k, p x of k, then in this case, if we see that this implies that t is equal to log s, then mx of log s is the sum k equals 0 to infinity e to the k log s px k. This here is exactly s to the power k. This is equal to the generating function, the probability generating function. Okay, so gx is the probability generating function. And remember the way that we use the probability generating function, much the same way as moment generating functions, the way the logic worked was we have expectation of ex to the s. The derivative here is expectation of s to the power x minus 1. Which was the sum from k equals 0 to infinity of k pk s to the k minus 1. And what we have is that we have uniqueness. So by uniqueness of coefficients in a power series, we must have that if two if two power series have all the same are equal, then they have all the same coefficients. If they all have all the same coefficients, then they're all equal. Right? So then what we have is that the function, the probability generating function of x of s equal to the probability function of y of s for all s in some region of 1. This implies that x is equal in distribution to y. Well, doing that gives us the uniqueness theorem for MGFs, moment generating functions, because if s minus 1 is with epsilon, is within s minus 1 is within epsilon, and then that means that there exists some, let's say, delta such that I'm sorry, the moment generating function of x is equal to the moment generating function of y for all t less than or equal to delta in absolute value. This is by the equivalence that s is equal to e to the power t. So s is close to 1 when t is close to 0. So this gives us a flavor. This gives us, first of all, a connection between the moment generating function, or the probability generating function, and the moment generating function. And it also proves the uniqueness theorem in the special case of a discrete non-negative random variable.